Hi, I'm Mark Barsamian. In this video, I'll be discussing predicates and quantified statements. This content is from section 3.1 in the book. Before we start, it's useful to review some notation for sets of numbers. This boldface capital R in our book, in some books, is typeset this way. That kind of symbol is called a double struck R or a blackboard bold R. The idea is that if you're writing with a pen or writing on a chalkboard, you can't do boldface, so how do you fake it? You draw two vertical lines instead of one, and that's where the term double struck comes. Anyway, this symbol stands for the set of all real numbers. There are some variations on this symbol that are accomplished by adding various superscripts. So this superscript asterisk means the set of all non-zero real numbers. The superscript plus sign means all positive real numbers. And of course, this superscript means non-negative real numbers, x greater than or equal to 0. A boldface Q is written this way when writing by hand. This is a set of rational numbers. I'll come back and say more about rational numbers after I talk about this symbol. This is the set of integers. Now back to the rational numbers. The rational numbers are the set of ratios of integers where the integer in the denominator is not 0. And the whole numbers, which could also be denoted z non-negative. So we handwrite the symbol for the integers as a double struck or blackboard bold z. Whole numbers, I'm not sure if I can do a double struck w. There's the symbol for the whole numbers. And then a couple of sets that I forgot to include. One is the natural numbers. So this is just the positive integers. And of course, I didn't mention that both of these, the rational numbers and the integers, can have the same superscripts that I put on the real numbers. And there's another set that I should have included, the complex numbers. But what we will primarily be interested in this course is this collection of sets with superscripts put on these integers and rational numbers symbols as well as the superscripts that we put on the real numbers. Another thing to recall is more recent from section 2.1. That's the idea of a statement form. It's an expression made up of statement variables and logical symbols, and it becomes a statement when actual statements are substituted in for the statement variables. So remember what a statement variable is. It's a variable that stands for a statement. So a statement form is a collection of symbols that represent statements. They're variables that represent statements, and also symbols that are logical symbols. And when you substitute in actual statements for the statement variables, the whole thing becomes an actual statement that's true or false. All right, so now to section 3.1. A new concept for section 3.1 is the idea of a predicate. So a predicate is a sentence that contains a finite number of variables that becomes a statement when specific values are substituted in for the variables. Now, in statement forms, we had variables, but those variables represented statements. They were called statement variables. In predicates, variables can be all sorts of kinds of variables. So for the variables, there's going to be the idea of the domain of a predicate variable. It's going to be the set of values that can be substituted in place of that variable. So a predicate is like a statement form in that it's got some variables in it, and once you substitute in actual things for the variables, the predicate becomes an actual statement, just as with a statement form. once you substitute in actual statements, the statement form becomes a statement. The difference between a statement form and a predicate is that with statement forms, the variables have varieties of kinds of domains. Now we'll be interested in identifying the values of the variables that will make a predicate true. And so we refer to that as the truth set. So if you have a predicate and you have a variable that has a domain D, then the truth set is the set of all elements of D that make P of X true when they're substituted in for X. And that would be abbreviated this way: the set of all X in the domain such that P of X. So you speak this simple: the set of all X in D such that P of X. So this vertical bar is spoken such that. In our first example, we're going to study this predicate, A parentheses X. It's this sentence: X squared is greater than or equal to X. Is that true or false? Well, we don't know because we haven't chosen a value for X. We haven't even chosen a domain for X. So in this example, we're going to study this predicate with a variety of domains, and we're going to see what the truth set is for different domains. So in the first part of the example, we're going to let the domain set be this set of numbers. And the question is, what is the truth set of the predicate? Well, so that means that we have to study the numbers that are in this domain, substitute them in to the predicate, and see if they make the predicate true or false. So let's make a truth table. So there are the four statements that we get when we substitute in those values of X. And we see that those statements are all true. So the truth set is the whole set D. Before going on, notice that our truth table had a column here that was not filled with trues and falses, like in previous videos. Well, in previous videos, we were dealing with statement forms made up of statement variables that could be true, that could represent true or false statements. So all we had to have in the columns for the variables were T's and F's. But in predicates, the variables can have a variety of domains. So in this case, the domain was this set of numbers, so that's the thing that goes in the column for that variable. Now we're going to study the predicate A of X again, but this time we're going to let the domain be the set of all integers. And the question is, what is the truth set when that's the domain? Well, we need to study this by making a truth table again, but this time our domain is an infinite set, so we can't really list all the integers and test them all. So what do? Well, we have to think a little bit about how different kinds of integers behave when they're substituted into this predicate, and consider subsets of the domain where all the numbers in that subset sort of behave the same way. That's all very vague, so let's just dive into the truth table, and I think you'll understand it once I get started. So I'm going to divide my domain into these three sets: the set of X that are negative, the number X equals 0, and the set of X that are positive. Turns out that those are the three chunks of the domain that we need to study in order to figure out the truth of this, the truth set of this predicate. So let's imagine what happens when I take a negative X value and substitute it in to A of X. Realize that if you take a negative number, a number that's less than 0, and you square it, the result will be a positive number. And a positive number will always be greater than a negative number. So the inequality X squared is greater than or equal to X will certainly be true. Now let's think about this case. In this case, we have just a single x value that we can compute the square of. We get the square is the number 0. So this equation, or this inequality, is certainly true in this case as well. Now consider this case, when x is greater than 0. Well, that means that since x is an integer, and we know that x is greater than 0, that tells us that in fact x is greater than or equal to 1. Now there's my tendency to always write my inequalities with the lesser number on the left. So let's think about what happens when I take this inequality and play with it. Remember that when you multiply an inequality by a positive number on both sides, you get a new inequality that's true, and you don't have to reverse the inequality symbol. So we end up with this new inequality that's true. Hey, that's the thing that we are trying to prove. So let's write that up here. So look, in all three cases, we see that a of x will be true. So that tells us that the true set is the set of all integers. All right, so we've now seen two examples of domains for which the truth set is actually the whole domain. Let's do a little bit harder example. Let's let the domain be the set of real numbers. What's the truth set of the predicate in this case? Well, let's go back up and have a look at what we did on the previous page. Most of this will actually work in the case of real numbers. If I let x be any negative real number, then this is going to be true just because of the business of positive and negative. And if I let x be the real number 0, then this is going to work because 0 is still 0. But when I go down to this part down here, I've got a problem. I've got a problem with this little line here. Because what we did in this red circled computation relied on the fact that if we had an integer and we knew the integer was greater than 0, we actually knew that the integer had to be greater than or equal to 1. There were no integers between 0 and 1. So we could assume that the integer x was greater than or equal to 1, and then we were able to get through this whole calculation using that key fact. Well, we don't know that a positive real number is necessarily going to be greater than 1. We just know that a positive real number is going to be greater than 0. So when we make our truth table, it's going to be a little bit more complicated in this case. So when we make our truth table, instead of just having one big category for all the positive real numbers, we have to break it up into two chunks. The real numbers that are between 0 and 1, and the real numbers that are greater than or equal to 1. Now, for these numbers here, the calculation that we did on the previous page will work. So let's just do that right here in this row. So there's that same calculation that we did on the previous page. If I have a real number and it's greater than or equal to 1, x is greater than or equal to 1, then x is less than or equal to x squared will be true. Or I could say that x squared is greater than or equal to x will be true. Now let's focus on this new case. Consider that inequality. In this case, because this inequality, x is less than 1, is what's true, when I try my trick of multiplying both sides of the inequality by the positive number x, I get this inequality, that x squared is strictly less than x. So that tells us that the inequality that we're interested in will be false. So our truth set, the set of x values that make x squared greater than or equal to x true, will consist of those x values here and these x values, but not these x values, but it will include these x values. So let's describe that solution set in symbols. So in interval notation, it's all the x values that are less than or equal to 0, union all the x values that are greater than or equal to the number 1. If I wanted to make a number line picture of this solution set, it would probably help. So that's a picture of the solution set. You see that these numbers between 0 and 1 are not part of the solution set. All right, well, that's the last domain that we'll study for that predicate a of x. Now I want to talk about quantified statements. Remember that a predicate is a sentence, and it's a sentence about the variable x. The sentence is neither true nor false until you substitute in an actual value of x. It's often useful to make a summary statement about how many x's in the domain will make p of x true. In some situations, for a certain predicate in their domain, every element in the set D will turn p of x into a true statement. We saw 2 examples like that, our first 2 examples. In this first example, every element of the set D was in the truth set. In the second example, every element in the set of integers was in the truth set. In some situations, though, there might be no elements in the domain that'll turn p of x into a true statement. And of course, in many situations, it'll be useful to know if there's at least one element in the domain that will turn p of x into a true statement. Look at our last example. Notice that it's definitely not the case that every real number makes the predicate true. It's also definitely not the case that no real numbers make the predicate true, but it is the case that some real numbers make the predicate true. There's at least one real number. There's a bunch of them. There's an infinite collection of real numbers that make this predicate true. Statements about how many x in the domain make p of x true are called quantified statements. There are 2 types that are most used in math: universally quantified statements and existentially quantified statements. Here are the definitions. We'll start with the definition of universally quantified statement. The symbol that I will use is this one. It has this weird upside down capital A in front, and then this symbol, and then has a symbol p parentheses x that's also in a set of parentheses. Now the symbol that's used in the book is very similar, but the p parentheses x is not placed in parentheses. Also, the book's symbol has this little comma here. But the book's symbol and the symbol that I use are spoken the same way. It's spoken this way: for all x in D, p of x. Now, what are these symbols? Well, x is a variable with domain D, and p of x is a predicate with variable x. Now, what does this mean, this symbol? Well, it means that the domain D has the property that every element in D, when you substitute it into predicate p of x, will turn p of x into a true statement. So notice, that's a statement about the domain D in the predicate. Now, if there is an element in the domain D that when you substitute it into the predicate turns p of x into a false statement, then this statement is false as well. This statement up here says every element of the domain will make p of x true. Well, if it turns out that there's an element in the domain that turns p of x into a false statement, then this is a lie. So if you do have an example of an element x in the domain that does this, that makes P of x a false statement, that's what's called a counterexample for this statement. Now, a little bit of additional terminology. This phrase, for all x in D, which is denoted by this symbol, this phrase is called the Universal Quantifier. Now I want to talk about the existentially quantified statement. It has this symbol, this wacky backwards capital E, and then another one of these x is an element of D symbols, and then the predicate P of x in parentheses. And the book's symbol is slightly different. So in the book's symbol, the P of x is not in parentheses. And instead of putting P of x in parentheses, there is this additional little phrase here. But both the book's symbol and my symbol are spoken this way. There exists an x in D such that P of x. Now what's the usage? Well, the usage is the same as with the universally quantified statement. X is a variable with domain D, and P of x is a predicate with variable x. Now what does this symbol mean? It means this. The domain has the property that there is an element in D, at least one, that when you substitute it into the predicate will make the predicate true. So as we noted with the universally quantified statement, this thing, this symbol is a statement, and it's about the domain D, and it's about the predicate. And some more additional terminology. This phrase, there exists an x in D such that, denoted by this symbol, this is called the existential quantifier. Now a couple of remarks. First of all, it's easy to see that a predicate is a sentence, but not a statement, because it contains a variable. The sentence is about x, and the sentence does not become true or false, that is, the sentence does not become a statement until an actual value is substituted in for the variable x. What's less obvious is that a symbol like this universally quantified statement, is a statement and not a predicate. That's not obvious because, after all, the sentence does include the letter x. But the difference is that in the quantified statement, this thing, something is being said about the domain D and about the predicate P of x. The letter x is needed to construct that sentence, but the x is playing a different role in this sentence than it plays in the sentence of a predicate. We say that in a quantified statement, we say that the x is a bound variable. In this symbol, we say that x is a bound variable. And a bound variable is a different thing from a variable. So predicates contain variables, and quantified statements contain bound variables. Quantified statements don't have variables in the same sense that a predicate has a variable. So for our first example of a quantified statement, we're going to revisit the predicate that we had before. So the first example is this. Let A be that statement. So notice in this statement, the domain is the set of integers, and the predicate is that inequality. Now, this is the same domain and predicate that we studied a few pages ago. This statement is a statement that says every element of the domain makes this predicate true. Well, let's go back up and look when we studied this before. It's a few pages up. On this page, we considered this predicate, x squared greater than or equal to x, and we considered this domain, and we found out that the true set was the set of all integers, the whole domain. So every integer that we chose in the domain made the predicate true. So this statement is true. So in that earlier example, since we found that for that domain of the integers in that predicate, the true set was all the integers, that is all of the domain. So that means that this universally quantified statement is true. Let's go on. Now here is the same predicate but a different domain. This universal statement is saying that no matter which x value you choose in the domain of real numbers, that x value will make the predicate true. But wait a second, we found earlier that this was not really the case. Let's go back up and look at what we studied earlier. In this example, we were using the same predicate. The predicate is x squared greater than or equal to x, and the domain was this set of real numbers. And we found that the true set was this green set down here, not the whole number line. In other words, there are x values in here that don't make the predicate true. So let's present a particular example that shows that there are x values in this domain that do not make this true. Notice that when we substitute this example of an x value into the predicate, we get this inequality, which is false. So that number, x equals 1/2, is a counterexample that demonstrates why that universal statement is false. So the universal statement is false, and the counterexample, x equals 1/2, shows that it's false. Now let's look at this quantified statement. There exists an x in the integers such that x squared is greater than or equal to x. Well, yeah, there definitely is. We just need to show one. So this existential statement says there's at least one x in the integers that makes that predicate true, and that's definitely true. So this quantified statement up there is a true statement. Demonstrate why we know that's true by giving an example, because this statement says there's at least one, so we just gave an example of one. Now, what about this statement? There exists an x in the real numbers that makes that predicate true. Well, this is also true. In fact, the same example, letting x equal 2 to demonstrate, works for this as well. So let's recap. Earlier, we found that when we are looking at this predicate in the domain, the set of all integers, the true set was the set of all integers. Every integer makes that domain, or makes that predicate true. But when we were looking at the same predicate with the domain being the set of all real numbers, not every real number made the predicate true. The true set was this subset of the real numbers. So when we come down to these quantified statements, this quantified statement about integers and the predicate, this quantified statement is true because every integer makes that predicate true. But this quantified statement is false because there is an example of a real number that does not make the predicate true. So those universal statements, one of them was a true universal statement, and this universal statement was a false universal statement. But the existential statements are both true. There does exist an integer that makes the predicate true, a whole bunch of them. So this existential statement is true about the integers and that predicate. And this existential statement about the real numbers and that predicate is also true. There is an example of a real number that does make the predicate true, just not all of the real numbers. Now, what about this statement? There exists an x in the integers such that x squared is less than x. This says there's at least one integer that makes that predicate true. Well, this is false. We've already determined that every integer makes this inequality true. So if that inequality is true, then this inequality cannot be true. This inequality up here would be false. So this is an existential statement that's false, and it's because there is not a single element in the domain that will make the predicate true. Remember, the existential statement just says there is at least one element of the domain that makes the predicate true, but no, in this case there aren't any at all. So the existential statement is false. Now I want to talk about quantified conditional statements. Remember that a conditional statement is a statement of the form if P then Q. Now think about this sentence. Most of you would probably say that this is a false statement. For instance, the number x equals -7 is less than or equal to 5, but -7 squared is 49, which is not less than or equal to 25. But in the context of this course, the sentence above is not a statement. It's a predicate that contains the variable x. So the sentence does not actually become true or false until we substitute an actual value in for x. Let's name this predicate. Let's let p of x be this predicate. If x is less than or equal to 5, then x squared is less than or equal to 25. And we can abbreviate that in symbols. We can say x less than or equal to 5, arrow, x squared less than or equal to 25. Now, you have to be careful to not write this. What's wrong with this symbol? Well, p of x, that symbol stands for a sentence. We don't use the equal sign between sentences. This mathematical sentence would say p of x is equal to x is less than or equal to 5, and then arrow. So this doesn't even work as a string of mathematical symbols. So don't say that p of x equals something. Notice that I always say things like this. I'm going to let p of x be some predicate. I don't say that p of x equals some predicate. All right, so we have this predicate, p of x, and it's denoted in words that way and in symbols this way. Let's make a truth table for p of x. Now, how will that work? Remember that p of x is this whole predicate here. So we need to build a table that has a column that's that. So in fact, we know that's going to be our final column. So let's go ahead and put that column in at the very right of our truth table. So we want to find out the truth value of that. Well, in order to get the truth value of that, we're going to need to have the truth value for these things first. So we need to have columns for those. Now, in order to get truth values for those things, we're going to need to know what x is. Now the question is, what x's do we need to put in this column? We should think about what x values will cause these things to be true or false. Turns out that the x's that we should consider are these three sets of x values. So the x's that are less than -5, the x's that are between -5 and 5 inclusive, and the x's that are greater than 5. So let's see what they do to the things in these other columns. So notice that if x is less than -5, then x less than or equal to 5 will be true. If x is in that interval, then this inequality will be true. But if x is greater than 5, then this inequality will be false. Now let's look at this column. If x is less than -5, then the statement x squared less than or equal to 25 will be false. So for instance, if x is -6, x squared will be 36. That's not less than or equal to 25. So for these x values, this inequality is false. Now let's think about these x values. If I take an x value in that interval and I square it, I'm going to get a result that is less than or equal to 25. So this will be a true here. Now let's consider x's that are in this set, x's that are greater than 5. If you take an x that's greater than 5 and you square it, the square is going to be greater than 25, so that inequality would be false. Now let's think about what goes in these cells. True arrow false is false. So you see that this predicate is not always false. There are some x values that actually make this predicate true. So let's go back to the start of this discussion. Coming into this course, most of you would have looked at this statement here and said that it's a false statement. But in this course, that thing there is not a statement, it's a predicate. And it turns out that it's a predicate that can be true for some x's and false for some other x's. So, summarizing, we see that there are some values of x for which p of x is false. And again, we already knew that, like the number x equals -6 is an example that shows that p of x can be false. But there are some x values for which p of x is true. So again, p of x is a predicate. Now, so that means that, from what we've seen, we can't say for sure whether p of x is true or false because it contains a variable. But there are some quantified conditional statements that we can build involving the predicate and that do have a definite truth value. So this existential statement is true. There is an x in the real numbers that makes that conditional predicate into a true statement. But this universal statement is false. If I say these words, every real number makes this conditional predicate into a true statement. If I say those words, then I've lied. It's worth returning to the sentence that started this discussion and summarize what we've discussed about this predicate. So this sentence started this discussion, and what it means to most people is something, most people would say that that sentence is false because, for instance, if you look at the number x equals -7, then that's a number that's less than or equal to 5, but -7 squared is not less than or equal to 25. So most mathematicians would say this is false. Well, most students. But what it means in our course is a predicate that can be true or false. Now, what about this thing that we built, this universal statement? Most students would look at that and not know what to make of it, but we look at it and we know that that actually is a false statement. So it's important to know that to keep in mind that in our course, a sentence like this contains a variable and it's got to be interpreted as a predicate. But outside of this course, it's important to keep in mind that to most students, to most people, a sentence like this is really meant to mean what we would express with this sentence. What we will call this idea is that when most mathematicians write this symbol, the quantifier is implicit. That is, when most mathematicians write this symbol, what they are really meaning is this. And that's why most mathematicians or most students would say this is a false statement, because what they're really thinking about is what we mean when we write this. So we distinguish between these two things. For us, these two things don't mean the same thing. The first thing is a predicate that can be true or false, and the second thing is as a statement that's definitely false. Whereas most students of math would look at this and say, oh, that's false, and they don't know about this idea down here. Now I want to talk about equivalent forms of universal and universal conditional statements. Let's let x be a variable with domain this set of integers. And let's let p of x be, actually I'm going to change this predicate. P of x is the predicate x squared greater than 0. Let's make a truth table for this predicate. We see that the important batches of x values to consider are all the negative x values, all the positive x values, and the x value x equals 0. When you think about what they do when you substitute them into the predicate becomes true for these x values, becomes true for these x values, but it becomes false for x equals 0. So any non-zero integer x will make p of x true. So we can express that observation with this universal statement. Remember that z star or z asterisk means the non-zero integers. So this universal statement says, for all non-zero integers, x squared is greater than 0. But we can also express the observation with this universal conditional statement. So the universal conditional statement says, for all x in the integers, if x is not 0, then x squared is greater than 0. So these two statements are both about x values that have two qualifications. The first qualification is that x has to be in the integers, and the second qualification is that x has to be non-zero. In the universal statement, that is in this statement up here, both qualifications are ensured by using the domain z star. But in the universal conditional statement, one qualification is ensured by using the domain z, and the other qualification is ensured by having the hypothesis stuck in there that if x is not equal to 0. It might seem like the universal statement is the better way of expressing the observation that we're trying to express because it's more concise. Look, this sentence has a lot less clutter in it than this sentence. Usually in math you want to be as concise as you can because clutter doesn't help. But it will turn out that there are situations where the universal conditional statement is actually more helpful. When we get to the part of the course where we're building proofs, it'll turn out that having the statement expressed in universal conditional form will often make it easier to frame a proof structure. We're going to be proving things in coming weeks. So in your homework exercises, you have a problem that involves rewriting a universal statement as a universal conditional statement. And that's what this is about, this idea that you can take something which is very concisely written in a universal statement and rewrite it in a less concise way as a universal conditional statement. Like this concise universal statement, for all non-zero integers, x squared is greater than 0. We expressed it in a less concise way. For all integers, if x is not 0, then x squared is greater than 0. That's the universal conditional form. That's the end of the video. Thank you.